Swayam Prabha. Digital India. Educated India.
Dear all, I am Professor Srikanth from Sastra Deemed University. I belongs to Department of Mathematics. My designation is Professor and Tata Realty Ramanujan Research Chair Professor. My area of specialization is number theory and allied areas like mathematical modeling and data science and so on. Now, I am going to give a introductory talk about that mathematical for artificial intelligence and machine learning. Now, we are going to deep of the course objective and other areas. Now, we have a mathematical foundation for AI and ML, means artificial intelligence and machine learning, and this having a lot of mathematical foundation. The special foundation for mathematical foundation of AI and ML is linear algebra, and then probability and distribution, continuous optimization, central machine learning ideas. So, the learning idea of linear algebra is understanding the fundamental concept in linear algebra, analytical geometry, matrix decomposition in machine learning. For probability and distribution, analyze the concept of probability and distribution, apply linear regression techniques for predictive analysis. For continuous optimization, apply principal component analysis for dimensionality reduction and optimization in machine learning. Based on these fundamental, we can easily understand the beauty of central machine learning. This central machine learning acquires a working knowledge of various AI and ML. Now, this figure shows that the foundation of 4 pillars of machine learning. The 4 pillars are regression, dimensionality reduction, density estimation and classification. For regression, we should have a strong foundation in vector calculus and linear algebra. For dimensional reduction, we know the fundamental idea of probability and distribution and some basic analytical geometry, as well as it is based on density estimation, as well as we have to discuss deeply about the optimization. So, optimization want to do, we have to further study matrix decompositions. So, these are all the pillars of machine learning. Then it will be very helpful to understand what is machine learning and artificial intelligence. Now, the inner part of mathematical foundation of AI and ML are, we have to cover the 4 units. The unit 1 consists of linear algebra, and linear algebra having a subdivision of system of linear equation, matrices, solving system of linear equations, vector spaces, linear independence, basis and rank, and then linear mapping and affine spaces. For unit 2, we have a topic of analytical geometry. It consists of norms, inner product, length and distances, angle and orthogonal, orthonormal basis, orthogonal complement, inner product of functions, orthogonal projection, rotations are the areas of very fundamental idea about the analytical geometry. Once a person can understand these ideas, they can easily do the matrix decomposition like determinants and trace eigenvalues, eigenvectors, Cholesky decomposition, eigen decomposition, diagonalization, singular value decomposition, matrix approximation and matrix phylogeny. So, these are all the subdivisions belongs to analytical geometry. Next topic is for unit 3 probability and distributions. It consists of construction of probability space, discrete and continuous probabilities, sum rule, product rule, Bayes theorem, and then it follows with the summary statistics and independence, and then Gaussian distribution, conjugacy and exponential family, change of variables and inverse transform, and followed with these ideas we have a continuum optimization. So, continuous optimization. So, this is consists of optimization using gradient descent, constraint optimization and Lagrange's multipliers and then convex optimizations. So, these are all the topic we have to be covered. And unit 4 consists of linear regression and it based on the problem formulation, parametric estimation, Bayesian linear regression and maximum likelihood as orthogonal projection, and then dimensional reduction with principal component analysis, and then problem setting, maximum variance perspective, projection, perspective, eigenvector computation and low rank approximation and PCA in high dimensions, key steps of PCA in practice, latent variables and latent variable perspective associated with machine learning and artificial intelligence oriented problem we have to discuss. So, these are all our main objective of the course Mathematics Foundation of Artificial Intelligence and Machine Learning. One may start to read this topic, they have to refer the following references. Number 1, by Mathematics for Machine Learning by Dyson-Roth, associated with the authors Faisal and Chen Soon Ong. And another topic is Introduction to Applied Linear Algebra Vectors, Matrices and Least Squares, written by Boyd and Vandenberghe. So, this is published by Cambridge University Press, the year 2019. And another book is Probability and Random Process and published by T. Veerarajan and publisher is Tata McGraw-Hill in the year of 2018. And another book is Foundation of Data Sciences and written by Ravinder Kannan and Avrim Bloom in the year of 2018. So, these are all the important books to refer to understand the beauty of Mathematics Foundation for AI and ML. For first topic, I am going to cover, these are all the ideas of lesson plan. I started with linear algebra and corresponding I have to introduce the system of linear equations. Then I will discuss matrices and then solving system of linear equations. Based on this we have to discuss a lot of problem, and then once you understood this area, then we have to go to the vector spaces, linear independence, basis and rank, problem on vector spaces, comma linear independence and comma basis and rank, and followed with that linear mappings, affine spaces, and followed with that problems on linear mapping and affine spaces, and some more problem we have to discuss related to linear algebras. So, these are all the small introduction about mathematics foundation for artificial intelligence and machine learning. Now, let us go into the deep of the introduction and motivation of AI and ML. So, machine learning is about to designing the algorithm that automatically extract valuable information from data. The emphasis here is on automatic, that is machine learning is a concern about general purpose methodologies that can be applied to many data sets. While producing something that is meaningful, there are three concepts that are at the core of machine learning: data, a model and learning. So, these things are the core of machine learning. Now, let us start with the data. Since machine learning is inherently data driven, data is at the core of machine learning. The goal of machine learning is to design general purpose methodologies to extract valuable patterns from data, ideally without much domain specific expertise. For example, given a large corpus of document, example books in many libraries, machine learning methods can be used to automatically find relevant topics that are shared across documents. One may refer Hoffman et al. In the year of 2010. To achieve this goal, we design models that are typically related to the process that generates data. Similar to that data we are given, for example, in a regression setting, the model would describe a function that maps inputs to real valued outputs. To paraphrase Mitchell in the year of 1997, the model is said to learn from data if its performance on a given task improves after the data is taken into account. The goal is to find good models that generalize well to yet unseen data, which we may care about in the future. Learning can be understood as a way to automatically find patterns and structures in data by optimizing the parameters of the model. So, the inference is one may know the pattern and sequence, then they may find the structures. Based on the structure, we can relate it to expression, the expression related to equation, and then the equation is based on the what? Upper bound, lower bound and equal to, that is less than, greater than or equal, and based on that we have to find out the feasibility of the solution. Ultimately, we have to obtain what? Optimization of the parameter of the model. So, that is what we have discussed, the optimizing parameter of the model, that is a learning. So, a challenge we face regularly in machine learning is that concept and words are slippery, and a particular component of the machine learning system can be abstracted to different mathematical concepts. For example, the word algorithm is used in at least two different senses in the context of machine learning. The first sense, we use the phrase machine learning algorithm to mean a system that makes prediction based on input data. We refer to these algorithms as predictors. In the second sense, we use the exact same phrase machine learning algorithm to mean a system that adapts some internal parameters of the predictor so that it performs well on future unseen input data. Here we refer to this adaptation as a training a system. So, this is the two important things of the sense we have to use for the machine learning. So, a model is typically used to describe a process for generating data similar to the data set at hand. Therefore, a good models can also be thought of as simplified version of the real data generating process, capturing aspects that are relevant for modeling the data or extracting hidden patterns from it. A good model can then be used to predict what would happen in the real world without performing real world experiments of the problems. So, that is most important to create the problem. In general, vectors are special objects that can be added together and multiplied by scalars to produce another object of the same kind. From an abstract mathematical viewpoint, any object that satisfies these two properties can be considered as a vector. Here are some examples of such a vector objects. So, geometric vectors. These examples of a vector may be familiar from a high school mathematics and physics. Geometric vectors, the following figure 2.1a are directed the segments which can be drawn at least in two different dimensions, right. Two geometric vectors x and y can be added such that vector x plus vector y equal to vector z in the another geometric vector. Furthermore, multiplication by a scalar lambda into x vector, where lambda is a scalar which belongs to a real number, is also a geometric vector. In fact, it is the original vector scaled by lambda. Therefore, the geometric vectors are instances of the vector concepts introduced previously. Interpreting vectors as geometric vectors enable us to use our intuitions about direction and magnitude to reason about mathematical operations. So, this is the picture what we have described earlier. Figure 2.1 of A represent geometric vectors. So, this is one x vector and y vector. Then if you add then x plus y vector will come. For a polynomial, it represents like this. See, y of x, y equal to f of x, which is equal to a naught x power n plus a1 x power n minus 1 and so on a n, provided the highest coefficient of x power n is not equal to 0, then it is a polynomial of degree n. Now, you see this is a polynomial that represent this, also we can do with the help of the vectors, and then we can associate it with the third vector like this. So, this is what we demonstrated earlier. Now, which is be added together, which result another polynomial, and then can be multiplied by a scalar lambda in R, and the result is a polynomial as well. Therefore, the polynomials are rather unusual instances of vectors. Note that the polynomials are very different from geometric vectors. While geometric vectors are concrete and drawings, polynomials are abstract concepts. However, they are both vectors in the sense and previously described. And third point, audio signals are vectors. audio signals are represented as a series of numbers. We can add audio signals together and their sum is a new audio signal. If we scale an audio signal, we also obtain an audio signal. Therefore, the audio signals are the type of vector 2. The fourth point, elements of R, that is n tuple, n dimensional of a real space or a vectors. Then R power n is a more abstract than polynomials, and it is the concept we focus on this book. For instance, alpha is equal to vector 1, 2, 3, which belongs to 3 tuple, is an example of triplet of numbers. So, adding 2 vectors a comma b in R power n component wise results in another vector. If you add a plus b equal to c in R power n, moreover a in R power n, lambda in R power 1 results and a scaled vector lambda a in R power n. So, for one tuple to n tuple also the same will reflect. So, that is the meaning of what a tuple of n dimensional we can expand it and then we can confine to 1 to n. Now, this is the system. We have to understand the mapping of the concept with the help of the chapter wise we described. So, these chapter you have to take into account so that you can understand the beauty of foundation of mathematics in AI and ML. So, let us start with the vectors. The vector is composes to the matrix, and also we have to learn the vectors with the help of the properties, and once you learn the property whether it is a linear independent or dependent, once it is understood the linear independent dependent, check it out the maximal set. So, a person can understand the linear independent dependent whether it is a basis or not. Once you understood this, you can go to the dimensionally reduction. But if you know the vector, you have to easily solve, therefore convert into matrix. Matrix is nothing but operator. So, any expression or equation convert into the rectangular array of rows and columns. So, matrix is operator. Once you can understand how to convert the operator, and then you can easily associated with vector and calculus is a vector calculus can understand. So, after learning the vector calculus, we can go into the depth of other area of mathematical tool. Now, once you learn the matrix having a lot of subdivisions to understand the solving the problem. One is a system of linear equation that can be represent the matrix, and then once you get the system of linear equation, we have to solve the unknown variable. That unknown variable solved by method of Gauss elimination method. Like that, plenty of method is there that you have to search. You know the system of linear equation, then if you have a system of linear equation Ax equal to b, right, Ax equal to b, then x equal to A inverse b. So, you have to know the A inverse, right. So, that is also most important. So, once you know the inverse of the matrix, then matrix inverse you have to learn. After learning this one, you have to understand the ideas related to ML and AI, that is linear affine mapping also you have to learn, so that you can incorporate it with analytical geometry and classification about this representation of the matrices. So, these two adding together, that is basis and linear or affine mapping, and we can do further classification. So, once your person learned all these things, then you would have been come across dimensionality reduction, then the classification further you can understand. So, this is the system of linear equation we are going to discuss. Apart from that vector spaces, we have to understand some basic idea of the group theory, and group theory consists of 4 laws as well as associated with abelian. Therefore, commutative group or abelian group, then you can easily understand the depth of the vector spaces. So, this is the map of one step to the another. Now, once you have learned this linear algebra, so it plays an important role in machine learning and general mathematics. The concept introduced in this topic are further expanded to include the idea of unit 2. Further, we will discuss the vector calculus, and where a principal knowledge of a matrix operational is essential. In unit 4, we will use the projections and to introduce in the section and dimensionality reduction with the principal component analysis. Further, we will discuss the linear regression, where the linear algebra plays a central role for solving the least square problems. Now, let us start with the system of linear equation. Example 2.1, a company produces the products N1, N2 and so on Nn, for which the resources R1, R2 and so on Rm are required. To produce a unit product Nj, Aij units of resource Ri are needed, where I equal to 1 to m and j equal to 1 to n. The objective is to find an optimal production plan, that is a plan of how many units xj of product nj should be produced if a total of bi units of resource Ri are available and ideally no resources are left over. So, this is the base. So, if we produce x1, x2 and so on xn units of the corresponding products, we need a total of ai1 x1 and so on ain xn. Many units of resources are I and optimal production plan x1, x2 and so on xn in Rn. Therefore, it has to satisfy the following system of equations: a11 x1 and so on a1n xn equal to b1 and am1 x1 and so on amn xn equal to bm. So, where aij belongs to R and bi belongs to R. So, this is the introduction of system of linear equation. Now, we have a equation 2.3 is a general form of system of linear equation, and x1, x2 and so on xn are unknowns of this system. So, every n tuple x1, x2 and so on xn belongs to R power n that satisfy the equation 2.3 is a solution of the linear equation system. For example, the system of linear equation x1 plus x2 plus x3 equal to 3, call it as 1, x1 minus x2 plus 2x3 equal to 2, call it as 2, 2x1 plus 3x3 equal to 1, call it as 3. Now, you see this system of linear equation, it has a no solution, because if you from the third equation to rest of the equation, and if you adding first two equation, this yield 2x1 plus 3x3 equal to 5 will come, but which is a contradict to the third equation. Therefore, it has a no solution. Like that, we can easily predict from directly seeing the equation, and we can identify that. As a third example, we consider x1 plus x2 plus x3 equal to 3, x1 minus x2 plus 2x3 equal to 2, 2x1 plus 3x3 equal to 5. Now, you have to add first two equation, you get the third one, and we can omit the third equation, the redundancy. From 1 and 2, we get 2x1, 1 and 2 you take it, 2x1 equal to 5 minus 3x3 will come, and 2x2 equal to 1 plus x3 will come. Now, you see that if you choose x3 equal to a, which is belongs to any real number and as a free variable such that we have to substitute backtrack, we have a triplet or the solution to the equation is 5 minus 2 minus 3 by 2 a comma 1 by 2 plus 1 by 2 a comma a. So, the triplet will come and we can easily find the solution to the problem, which is a solution, and it has a infinitely many values of this system of linear equations. So, like that we can find out whether the equation having a solution or not, or finitely many or not, or infinitely many or not, or it has a no solution or not. Like that we can easily find out the solution to the problem. Now, we have a note. So, the geometrical interpretation of the system of linear equation is, in a system of linear equations with the two variables x1, x2, each linear equation defines a line on the x1, x2 plane. So, we have to take two planes x1 and x2. Since the solution to the system of a linear equation must satisfy all the equations simultaneously, the solution set is the intersection of these lines. So, this intersection set can be a line if the linear equation describe the same line, a point or empty. So, when the lines are parallel, an illustration is given in the figure 2.3 for the system shows that the solution space of a system of two linear equation with the two variables can be geometrically interpreted as the intersection of two lines. So, every linear equation represents a line, you know. Now, you take these two equations, solve them, and then you can get the value of x1, x2 as 1 comma 1 by 4. So, that is the solution of this system. Therefore, if you take these two lines, draw it for first line 4x1 plus 4x2 equal to 5, in a blue lines represent, that is the equation of the first one, and red line represent 2x1 minus 4x2 equal to 1. Now, you join these two, what happened? The intersection point will come, that point is called as 1 comma 1 comma 1 by 4. So, after solving this, we have a common point between the two equations of the line, where the solution space is the point of x1, x2 equal to 1 comma 1 by 4. Similarly, for three variables, each linear equation determines a plane in a three-dimensional space. When we intersect these planes, that is satisfy all the linear equations, at the same time we can obtain a solution set, that is a plane. So, a line, a point or empty may come. So, that is the interpretation of intersecting of the two lines, and what are all the feasible point may get it, whether it has exactly one solution or infinitely many solution or no solution, like that we can determine. But this equation having one intersection point, definitely it has a solution. So, the plane have no common intersection, like that we can easily fix it. So, for a systematic approach to solving the system of linear equation, we will introduce useful compact notation. We collect the coefficient aij into vectors, collect the vectors into matrices. In other words, we write the system from 2.3 the following. So, already we discussed the 2.3 equation is the system of linear equation. There we can represent the matrix notation in terms of the coefficient of x1 as a column wise of a11 into am1 and a12 and so on am2, that is first row second column, and then go to nth row second column into x2 and then and so on and then first row nth column and then mth row mth column into xn, which is equal to right hand side is B1, B2 and so on. Bm is a non-homogeneous that represent the system in terms of the matrices. So, the matrices take the coefficient of A11, A12 and so on, A1n and then AM1 and so on, AMN. Therefore, it has a m rows and n column of the multiplication of the column wise of the unknown variable x1, x2 and so on xn, which is equal to B1, B2 and so on Bm. Now, to take it into account of this equation and then we have to consider a lot of ideas about solving the system of linear equation in terms of the matrices and check it out, the matrices A and then this is x, this is B and find the value of x using that A inverse into B. Then you have a inverse matrix A, you check it out, the inverse matrix is inverse exists or not using the singular or non-singular. If A is non-singular, then we have to proceed further A inverse. Now, you can understand the inverse of the matrix A and then multiply them with B and then you can get solution of x. Now, you have a system, this system having a unique solution or consistency solution or inconsistent solution or unique and finite solution or consistent and finite solution or infinitely many solution, like that we have to determine with the help of these matrices. So, that is the ideas we have to learn it.